Thank you very much for the invitation to be here. My wife and I are very happy to be here. A slide previously showed this business of the hot temperatures in Phoenix, but the comeback always is, but it's a dry heat. And when you leave Arizona, the rest of the world is humid. So that's how we deal with that there. All right, the talk when it was originally scheduled was to cover both brains and brawn, but just in the time interval since I was scheduled to be here, I've added so much more information to the brains talk that we had to just deal with that. So this is the actual talk you're going to get. Maybe if there's time in the question answer period, we can maybe deal with some of the muscle stuff as well. So here are some interesting things about the human brain. It attains the mature physical size by age 8. So you can see that there's a change in the ratio of the size of the head to the torso, starting at age 8 onward until the adult ratio is obtained. It finishes actually forming the synapses, the connections between the nerves, around age 24. So because that process really isn't completed until that age, that's how we can truthfully say that we deal with brainless teenagers. So here's an illustration showing the junction with one nerve to another, and that junction is called the synapse. So we're forming synapses as we go along and experience things, and we'll be talking about that a bit later on. I know some of you are medical professionals here, and you can tell me that the brain weighs about how many pounds? 3. And that's about 1.5 to 2% of the body weight. And it metabolizes 20% of the energy needed just to exist, not even to digest food, just to lay there and breathe and have your heart beat. The brain uses 20% of the energy required just to vegetate. It's quite a bit. These are the different things we're going to talk about as we go through this, and we'll start with perfect optimization. So engineers and electricians use the save wire principle. In other words, be conservative and use the minimal amount to connect things. So things need to be optimally arranged. So this architecture of the brain employs the same principle at various levels, whether it be local levels, regional levels, or the entire brain. The save wire concept is employed. And there is even mathematical precision to the distribution of the neurons. And so this graph shows the equations for these relationships in terms of distances. And this shows that this is exquisitely well designed. And a quote here, it is a convenient and useful model for measurements in exact and engineering sciences, as well as medicine, economics, and other topics. So this is clear evidence that this is not some random chance events, how this wiring took place. It had to be extremely well designed. And as I mentioned, there is regionalization of functions, and here you see color coding for different parts of the brain for different activities. So for example, the pink part is the front of the brain, and that pale yellow part is the backside. So your visual cortex, the part that deals with the information coming from the eyes, actually is processed in the very rearmost part of the brain there. And you see these other locations for the other functions that are shown in this diagram here. So this is very well organized, compartmentalized functioning and computation and use of the information that comes to the brain. And then a physical landmark is what's called the central sulcus. Sulcus means trough. So this is the trough that divides the motor part of the brain in front of the trough from the sensory part of the brain behind the trough. And there are different kinds of neurons, nerve cells, and the large one there that you see is kind of a pale orange color is the one that does the work of computing and thinking and making decisions. And that is a very long cell. So it starts in the brain, goes down into the spinal cord, and then we'll connect with a second cell that goes from the spinal cord all the way down to the tips of your fingers or the toes. So those are extremely long cells. And they have the insulation wrapped around them by letter B there on the left-hand side of the slide, oligodendrocyte. And that word means, oligo means few, dendro refers to branching, as in trees, and cyte means cell. So what it means is cell with few branches. In contrast to the neurons, which have thousands of branches, so they can connect with many, many, many other cells. But the oligodendrocyte's job is to make that jelly roll insulation, myelin, different types of specific fats that insulate the nerve as it travels down the length to its destination. And it's just like having the copper wires in buildings that are insulated by either plastic or rubber. These oligodendrocytes perform that function. And then you see letter C, astrocyte. That literally means star cell. And so it has these branches that make it look like a star. And it is the connecting cell between the blood supply to the brain with the capillaries there, then connecting to the neurons. So anything that needs to get into those neurons from the blood has to go through the astrocyte. And so collectively, all these astrocytes, and there's zillions of them, form what is called the blood-brain barrier. And so this is a protective mechanism so that types of molecules that are in the blood that should not get into the brain don't. And this is based on polarity, that molecules that are polar will not get through unless there are special gates, special channels that allow those to get through. Then the other thing about the astrocytes is they deal with the creation, the orchestration of new synapses, new connections as you gain experiences and form memories. Then letter D is the ependymal cell there. And within the brain, I'm going to show you in a bit the picture of the fluid-filled structures inside the brain. And those are called ventricles. And these cells line those ventricles and form the cerebrospinal fluid that cushions the brain and gives it protection. So when there's a blow to the head, there's some protection there with that fluid in between the skull and the brain. Now, many of you ladies have something around your neck which may have something dangling from like a chain, right? Yes? Okay, what are those called? Pendants, right? So they're pendants. So they are hanging from the neck. So something is pending, it is in process, it's hanging. If it's depending, it's hanging upon. If it's e-pending, it's doing what teenagers do at the mall. What do? They're hanging out at the mall, right? So this word literally means, ependymal means hanging out. So these cells hang out into the ventricle where they form that cerebrospinal fluid. And in letter A, microglial cell, those are the immune system representatives in the brain and spinal cord, the central nervous system. And so they do the job of protecting against infection in the brain and the spinal cord. Then letter E here, which I added to this original diagram, is a relatively recently discovered type of cell called the boundary cell. And the boundary cell, it is what is used to mark the beginning and the ending of an event. So it's like a time stamp, that this is when this event happens, when it starts and when it stops. So an analogy here is you see a film strip, that is the event itself, and the event is recorded by event cells. And the boundary cells put the time stamp for the beginning and the end so that you can know when this event happened. So when the brain files things away, you remember what order things happened as they are recorded by those new synapses that form. Another interesting type of cell is called a rose hip neuron. And you see there the picture of the structure on rose bushes. They have that shape, and that's why this neuron is named, because it has the same shape as the rose bush there. And this one serves the function of being an inhibitor regulating the flow of information. So I think that's probably so that there's not too much information processed at one time, so everything can be properly absorbed and then dealt with. Here is a headline from an article just for a couple of months ago. Artificial intelligence tool detects sex-related differences in brain structure. So artificial intelligence computer programs that process magnetic resonance imaging results, MRI scans, show differences in how the brains of men and women are organized even at the cellular level. There are differences. So these variations were spotted in white matter. That's the great part of the brain, except for the very, very superficial part, which is the gray matter. And I'm sure you've heard in school your teacher referred to use your gray matter, right? Well, that's where all those synapses are. That's where you're processing the information. The white matter is because of those oligodendrocytes, those sheaths insulating the cells with that fat look white. And so they're busy keeping the neurons from short-circuiting with each other. And so these variations between men and women are spotted in that white matter, fostering communication between the regions. So I'll give you a quote here from Genesis chapter 1. So God created mankind in his own image. In the image of God, he created them. Male and female, he created them. Scripture is very clear about this, and yet we see today so much of this stuff going on with gender confusion being promulgated in the schools. And Tuesday you can decide you're a guy, then on Wednesday you can decide you're a gal, and all this baloney. It is really sad to see this going on, but it has no biological basis. That's totally a construct by people who, I'll just say, want to create confusion and chaos. So it's true that ladies are from Venus and guys are from Mars, all right? And we literally are wired differently. And that's why there are times when as guys, we just don't understand how the lady is thinking. And my wife and I have that experience from time to time. And then she also wonders what in the heck I'm thinking from time to time. So there's a reason for this. We were created to complement each other, for each one to be able to pick up on things and deal with things that the other one was not built to do. And together we make that pair that God intended. The brain has vast computational power. It's amazing. So what I'm going to do is give you like a little crash course here on how the flow of the stimulation of the nerves working happens. So there's an arrow with this electrochemical signal that comes down the membrane that surrounds the cell, the nerve cell, the neuron. And then it comes to a place there where there's this channel that is built to open up and let calcium into the end of the nerve when that electrical signal comes down the pike there. And so when that calcium flows into the cell, it stimulates these vesicles which hold molecules which are chemical messengers, neurotransmitters, that travel across that gap, that space between the two cells there. And that's called a synapse or synaptic cleft. So those molecules of neurotransmitter then are released, cross the gap, and then they have receptors that are very specific for those particular molecules, exceedingly specific. And then when that happens, there's another set of gates that involve sodium and potassium, and then the new electrical signal is transmitted down the second cell. So that's how that is worked with getting that information from the first nerve cell to the second one, or from the first nerve cell to a muscle cell or to a gland. Now, in this particular junction between these two nerve cells, or nerve and muscle, there are about 1,000 of these neurotransmitter receptors. And consider each one to be a microprocessor. So this is saying that there are roughly 1,000 microprocessors at one synapse. And so here again is a reminder of that axon, that very, very long neuron. It can be 3 feet or even longer, going from brain to spinal cord and spinal cord to end of extremity. And there are many, many of these synapses, these connections. So we have roughly 200 billion nerve cells, these neurons, and there are hundreds of trillions of synapses with about 1,000 of these microprocessors at each synapse, at each junction, each connection. So this humongous number, the results, is why we have such vast computational power. It is so much that one human brain has more computational power than the internet. That should blow your mind. It's astounding, absolutely astounding. And then this is one of the many times I want to say, Mr. Evolutionist, please explain to me how this happened by random chance processes. So as I mentioned, the very superficial part of the brain is the gray matter, where all these synapses are happening, and the deeper part is the white matter, where that insulation is surrounding all of the neurons and keeping them from short-circuiting with each other as they go from place to place. So just one tiny little cubic millimeter. So a millimeter is, just this space between my fingers here. You can't even really see it. It's so tiny. Of brain tissue contains these numbers: 57,000 cells and 150 million synapses. Now that's just in one little cubic millimeter. Well, there are over 460,000 cubic millimeters in the cortex. So do the math and you get these horrendous numbers that are so big we can't even comprehend them. So this concept is attempted to be demonstrated with this blue part of this diagram being the cortex and the rest of it being the deeper layers in the brain there. So in the cortex, which the word cortex, by the way, means bark. So it's like the bark on a tree. It's that outside layer, which contains these humongous numbers of synapses and these microprocessors. So I love this particular headline, which is from a recent publication here. Biological masterpiece: evolution wired human brains to act like supercomputers. I think they got that part wrong. Well, scientists have discovered that the human brain inherently uses a type of inference called Bayesian influence. What this means is that it's a statistical method to combine what you already know with what you're learning, what you're assimilating, so that the two are put together, are combined, and then you have more useful ways of using the information that you have acquired. So a way of picturing this is, here is the brain with the information, the intelligence that it already has. So then new data is acquired and added to the previous data, and then that then is combined and increases the ability to have more information as your base to think with. And so that database grows and grows. So for example, you come across new data in the form of a butterfly and you say, well, I don't understand it, I don't know this yet, but you've already experienced a hummingbird. So now what you can do is add the new information that you're acquiring about the butterfly, combine it with what you know about the hummingbird, and you now have a larger database. So this is that Bayesian inference. As opposed to how computers work, which they just deal with ones and zeros, a tremendous sequence of ones and zeros of just sequentially, is it one or no? Zero, is it yes or no, yes or no, yes or no, a zillion times. Where we don't do that, we're able to compute adding a much greater amount at one time to incorporate it with what we already know. So the way we think is not at all like the computer. So you can see the computer is actually much more limited in its ability to process than we are. But when you give it enough time and enough data to work with, then it can do an awful lot. So in Romans 1:22, I really like this verse because as a professor at Arizona Christian University, where I teach the pre-med courses, this has a special meaning for me. Professing to be wise, they become fools. And I think this is so true of so many professors, not only in the US, but around the world, who teach things that are not consistent with Scripture. They teach things that are actually quite untrue, such as evolution. And what's the deal? Well, they've exchanged the truth of God for the lie and worshiped and served the creature rather than the Creator, who is blessed and forever. Amen. So I think this verse is very apropos for what's going on today. We have phenomenal processing speed. It was originally thought that all that processing took place in the soma, the body of the neuron. So that yellow disc that you see there to the left is the body, the soma of the neuron. That's where the nucleus is located. I'm indicating here by that black dot that I've just added. Then the axon is that long green part, and then the synapses between the red and the blue, the red being that part of that same cell and the blue the next cell. So the electrical activity in that soma is an all or nothing thing, spike, as is a digital signal. But there's all this activity in those dendrites where all of those microprocessors are located that we spoke of. And so it's a combination of analog and digital activity that's 10 times greater than in the soma. So we have a phenomenal processing speed that is more than 100 times faster than was previously thought to be the case. So we literally can compute and operate at warp speed. How about optimal energy efficiency? So as I mentioned before, just to vegetate, lay there and exist, doing nothing except breathe, have your heart beat, and just keep things going, not even digesting food, the brain uses 20% of the energy to exist. And that requires only 10 watts to function. And so this C7 light bulb, the kind we use to light up a hallway, a night light, is one that takes 10 watts to function. However, a robotic brain built to have the same capacity as the human brain, if it could be built, would require at least 10 megawatts, they have computed, which is the output of a small hydroelectric dam. So that's quite a contrast, how the human brain is far more efficient in its use of energy. So we have efficiency in energy use, we have efficiency in the save wire concept, the vast computational power, and the speed with which we can do this. Well, how about the capacity of memory? So petabyte is like 10 to the 15th. So that's 10 with 15 zeros after it, that huge number of bytes. And so 10 to the 6th is a million, to the 9th is a billion, to the 12th is a trillion, to the 15th quadrillion bytes. These are huge numbers. So that's the amount of memory capacity that we have. It's a huge amount. How do we store memories? So this is highlighting a particular part of the brain, a system called the limbic system, incorporating these structures that are in red and in blue. And in particular, one part of that total structure is the thing with the bulb at the bottom with that on that long tail. And that's called hippocampus. Hippo refers to horse, campus to monster. So we have the seahorse, a sea monster, as what this is named after, because you can see somewhat of a parallel in the structure of the seahorse and the hippocampus. So in this limbic system is where memories are stored. And this sequential unfolding of specific sleep rhythms is what coordinates memory consolidation while we sleep. So what's going on is, one of the big reasons we need to sleep is physical rest. But the other huge reason we need to sleep is to deal with everything that's happened since the last time we slept. And so this does the job of filing away all that stuff, organizing it and filing it away. And so there's a correlation with the type of brainwave activity and the work of doing this organizing and filing away of the information. And so at the top you see being awake with mental activity, in other words, engaging the brain, learning, reading, doing something like that. And then just awake and just resting, kind of vegging there. And then the pattern with sleeping, and then deep sleep. And it's in this deep sleep is when we do our filing away. So in the past, all these individual electrodes have had to be glued on to the person's head and scalp in order to pick up these electrical waves, these signals. But nowadays they have these beautiful caps where all the electrodes are on the cap. You just slip the cap on and you can get the, quote, brain waves. But there's even something that's more significant in terms of the depth at which the electrical signals are acquired. And that are these very tiny electrodes that are embedded deep inside the brain, usually in patients who have severe seizure activity which does not respond to medication. And these unfortunate people continue to have seizures even though they have optimal medication to try and stop the seizures. So it's been found that the location of the initiation of the seizure activity can be localized by these electrodes, and then these deep ones can be implanted. And here showing some CT scans showing the location of where these deep electrodes have been placed. Well, we've been able to benefit from this by being able to also measure the electrical activity in the brain with these deeply implanted electrodes. So while these patients were sleeping, their rhythms and the neuron firing rates were recorded. And these showed that the firing rates and the communication with the nerves were indeed orchestrated by these slow oscillations, these slow up and down signals. And that's when the work of doing the memory consolidation and filing away occurs in deep sleep. And there you are. So this is when we're making those new synapses, those new connections to file the stuff away, use those event cells, use those boundary cells, organize the stuff, and put it in the filing cabinet. So here's just a diagrammatic way of trying to illustrate that with these boundary cells dealing with starting, marking the start of it, the event cells recording it, and then boundary cells recording the end of that incident. So for example, there is the business of maybe someone walking into the room, or you start observing something, so that boundary cell fires and the event cells record, and then the boundary cells is labeled for the end of it to put the end to that particular memory. So that's how things are put in the right order, because there's time stamps in these boundary cells. Well, it's interesting because we're learning even more about how this happens. There's this particular very large protein here. This is an attempt at a three-dimensional representation of this protein called KIBRA, kidney and brain expressed protein. In other words, this protein is made in the kidney and the brain. And its job is to coordinate many other protein molecules that deal with the work of making these synapses, of forming them and hardening these memories so that they are recorded and retained, and especially long-term memories. Well, it's interesting that there's another protein that has this name, protein kinase zeta, and kinases are proteins that activate things by using phosphate groups, phosphorylating other proteins, using the energy in that process to have the other proteins do their job. And so what this particular protein kinase zeta does is it is a maintenance and repair protein to make sure that the KIBRA protein is kept in shape. Now, we all know from personal experience that our clothes wear out, our homes fall apart, our cars fall apart, and our bodies fall apart, right? It's the second law of thermodynamics. And that happens to this KIBRA protein, as with many other things in our bodies as well. Well, the job of the protein kinase zeta is then to maintain and repair the KIBRA protein so it can do its job to coordinate all the other proteins in that work of forming and consolidating and filing away memories. Mr. Evolutionist, how did that come about? By random chance events. So it maintains. It would be like the carpenter who repairs the barn. So when there's a problem with a particular board or slat, he replaces it and makes things like new again. Now research is going on trying to determine what other molecules represented by this yellow and gray representation here that would interfere with this process. I tried to find names of specific molecules, but I couldn't find them. But this kind of research is in process because, you know, there are significant numbers of people who have these problems of not being able to retain memories, especially as they age. And so this is being investigated so that we can find out maybe there's some way with dealing with this for these particular patients. So in Ephesians chapter 2, we have God who is rich in mercy. Before I read this, I want to say I've read a couple books that deal with recording what patients who have had near-death experiences have gone through, and they have temporarily been in heaven. And several of them have reported the situation where they've had their life reviewed for them with Christ, and that it's an exceedingly fast process. So I'm wondering if you know, what is with all this stuff being filed away in the brain, if we don't have a lifelong video camera that's recording everything, and Christ hits the play fast button, and we go through all of this, and that they have reported that that situation is not a judgmental situation, but he's simply letting them see where, as they have gone through their life, that he has demonstrated mercy and grace with various events that have gone on. So that's why I put Ephesians 2 here, 4 and 5. But God, who is rich in mercy, because of his great love with which he loved us, even when we were dead in trespasses, made us alive together with Christ. By grace we have been saved. And so I think this is what these patients who come back relate, is what has happened before they return. Master secretor of hormones and central cerebrospinal fluid. Okay, different parts of the brain make different hormones. Some of these hormones are protein molecules. They're what we call peptides. Some of them are quite short, or only 8 or 9 amino acids long, so those are called oligopeptides. Others of these hormones are steroid hormones. They are based from the cholesterol molecule. You know, all cholesterol is not bad. We need a certain amount of it to make our steroid hormones. So different parts of the brain make these different hormones, and you can see that this is a pretty significant list of these various types of hormones here. And I'm not going to go into them because that would be another 3 or 4 hours. But just to make the point that this is an exceedingly complex situation with a great number of these hormones that are very necessary for life. And not only that, there are feedback mechanisms to the brain so that it knows when enough has been made, when to stop, and when to start, so that there's control. You know, it would be like having an automobile factory just pouring out automobiles without any feedback as to whether there's a market for the product after a certain period of time or not. So all these feedback mechanisms occur for each individual type of hormone. And also mentioned the cerebrospinal fluid, this fluid that is made by those cells that are hanging out at the mall, the ependymal cells lining the blue part here, these ventricles, these fluid-filled parts in the brain, and then it flows through these series of canals, bathes the brain, gives that protective layer between the skull and the brain, and also down along the spinal cord to give it protection as well. Not only do they give physical protection, that fluid also provides nutrients for the cells with which it comes in contact. So this is showing that route through which the fluid flows from those 2 blue first ventricles. They're named lateral, and there's 2 of them. So the next one is the 3rd ventricle, connected by a canal, then the 4th ventricle, connected by a canal, and then the central canal that goes down along the spinal cord, like so. So I'd already mentioned to you the ependymal cells here. So again, they provide that cushioning and providing nutrients to the cells that they come in contact with. Where we play and laugh, and I'm not talking about the park or the playground here, but what part of the brain? Well, I just mentioned that canal that goes down through the spinal cord. Well, surrounding it is an area of this gray area, this gray matter, in other words, where there's a lot of synapses. Because in that brain stem, a lot of activity goes on that we are not aware of. For example, regulation of breathing, regulation of heart rate, of temperature. All these things happen automatically by the part of the nervous system we call the autonomic system. We don't even think about that stuff. We don't have to. Otherwise, every time we'd have to tell the heart, beat, beat, beat. But we don't have to, because that's all taken care of. So that's what's going on in these areas. And periaqueductal means the area around that canal that goes down the middle of the spinal cord. So this is the area they have discovered where things involving play and laughter occur. And so there you see the spinal cord going down, and here's a cross section through it showing the aqueduct, that canal, with that gray area around it. So that's where we do playing and laughing. Now this next thing is absolutely astounding. It's called the Mozart effect. And it is strongest in this one particular piece of music, a sonata written for 2 pianos. And it has a number, a K number. And that refers to a system of numbering Mozart works, which was done later on by a musicologist named Kezele. Because in Mozart's time, the composers didn't put numbers on their works. Later on, they started doing like opus 1, opus 2, opus 3, and opus is the Latin word for work, so that people could know the sequential order in which their compositions were created. So this particular one, Kezele 448, written for 2 pianos, has an amazing effect. So I'm going to show you that the 2 different groups, people who are really anxious about dealing with math and people not so anxious dealing with math in the green line. So exposing these 2 different groups to no noise, just to silence, you can see that the math scores are at those particular dots, a little above 80 for the people with low anxiety, and about, we'll say 15 for the folks with high math anxiety. Then the same folks were exposed to white noise, like fans that we put on to try and mask out background noise. And the scores went up to 25 for the high anxiety people and up to 80. Before I think I said above 80, above 60, I'm sorry. And then they're exposed to Mozart. And then the scores went even higher, above 80, we'll say about 85-ish towards 90, and way up to 80 with these folks with high math anxiety. You go, whoa, this is amazing stuff. Well, think about it in that music is really based on physics. The sound waves, the physics of the sound waves, and how music is organized and the rules, we'll talk a little bit about that, gives regular order, it gives organization to what is being heard and being processed by the brain. So it's somewhat mathematical. So here is another way of looking at the effect of Mozart's music, is this was dealing specifically with the idea of being able to deal with spatial relationships and be able to think of things like, how am I going to put all these different things into this particular size container? How they're all going to fit together, that kind of a thing. Spatial relationships. And you see here that with the green, silence, the score is about 110, and about the same, tiny bit higher maybe, with relaxation type music. But with Mozart, it went up to 120. Again, it's amazing, the results of this. So then musicians who spend their careers playing classical music, not just Mozart, but classical music in general, were highly investigated and scanned over repeated periods of time. And this showed, with the bottom line that's more of a gray-blue color, lavender maybe, that as they age, you see starting after 20 years of age and working up towards 70 years of age, doing sequential scanning, that the brain volume is shrinking. The brain shrinks due to cell death. The volume of the brain is smaller as more cells die as we age. But in these musicians who spent their career playing classical music, the amount of total shrinkage was quite minimal. And then when you look at the left-hand lower part of the slide, what actually happened in that cortex, that thin layer that's on the outside of the brain, it actually got thicker as they were exposed to the classical music over that period of time, which in some degree compensated for the shrinkage of the rest of the brain, for the total volume. Amazing, amazing stuff. So then, exposing people to either classical music written in the 1700s, 1800s, and some composers in the 1900s, you see here their ability to process, having information put in front of them, being able to process that information, cognitive ability, scored nearly at 80 for the ones with classical music, silence about 75 3/4, and then for rock music, a little over 75, even worse than silence. Isn't that amazing? I'm very glad that from my early teen years on, I did not like rock music. Now here's the most astounding thing. Back to the people who have this epilepsy, the seizure activity that cannot be controlled by medications. This particular work I mentioned, Kezele 448, after even just 30 seconds, so after 2 of these bar time spans, 0 to 15, 15 to 30, you see that there's a decrease in the amount of seizure activity going on in these patients who did not respond to medication with Mozart, with this work, 448. With the exposure to the prelude to the second act of Wagner's opera Lohengrin, there was a temporary increase in the seizure activity recorded, in the electrical activity for seizures, and then it went back down to the baseline. And then with violet music, not violent, but violet, then there was an increase in the seizure activity, then a decrease, and finally it leveled off just about a tiny bit below the original amount. So here is that Kezele 448. This is the one that had by far the best effect on seizure activity, this particular piece of music. Now the other things I talked about involved classical music in general. The second piece of music that had the next best effect on seizures was this sonata written for one piano, Kezele 545. Astounding how this it works. Well, let's compare the characteristics of these things in music, the natural rules of music, I say, due to harmonies, due to the physics, the structure, the proportion, the balance, and the mathematical logic. So we'll contrast classical with popular/rock. So popular/rock has narrow ranges, only one rhythm, the same rhythm from the whole song, can be deafening, especially in these rock concerts. Only one speed, tempo refers to speed, and it's short and highly repetitive. Same thing, over. To me, mind-numbing. Whereas for classical music, there's wide ranges of rhythm throughout the piece, wide ranges of dynamics, meaning it's soft or loud, or soft again, and up and down in volume. The speeds change, slowing up, speeding up, and it's a longer length and time. Usually most songs are about 3 minutes. Whereas with the longer length and with all these variations, there's time for the brain to absorb and to digest and analyze and soak in what's going on with that piece of music. So it stimulates, the intellectual activity. As opposed to the popular / rock music, and unfortunately, in my opinion, too many of these more modern songs we have in church, which other people call 7-11 songs, because it's the same 7 words 11 times. But even worse, some of these songs are 724 songs, same 7 words 24 times. All right. Well, not only with the intellectual capacity, but also the emotional and mental changes that go on. So here you see blue representing classical. Caring goes down a little bit, relaxation goes up, vigor goes up, hostility goes down, fatigue definitely goes down much more, sadness, a little bit more sadness, because some of the music is quite sad, and then tension definitely decreases. But look what happens with rock music. Caring goes way down, mental ability goes down, relaxation goes down, vigor goes down, hostility way up, fatigue up, sadness way up, and tension way up. And then there's New Age music, which is kind of interesting here. Mental activity, down. Relaxation, way up. Vigor, down. Hostility, down. Fatigue, up. Sadness, up. And tension, down. Pretty interesting. So it's important what we are exposed to. Well, in terms of hormones, music stimulates the brain's secretion of endorphins. Endorphins, this word is a portmanteau, meaning a word where parts of 2 other words are put together, or 3 words. So endogenous means produced from within. And orphan comes from morphine. So our brain secretes morphine-like molecules in response to stress the brain is exposed to, or the body is exposed to. So for example, you may have heard of the runner's high, these people who run these very long races, miles, kilometers long. After a significant time period, they develop this high feeling. Well, it's because when the brain's saying, okay, I'm being punished long enough, it puts out these endorphins, and that's how they feel this high feeling. And then enkephalins are another category. You can see their structure here is quite similar. All of the corners and angles represent carbon atoms, and then you see H for hydrogen, and then for nitrogen, and O for oxygen. So these are the structures. These are quite similar. So the brain secretes these in response to what it is subjected to. Well, it also secretes dopamine, which is a neurotransmitter, a different kind of neurotransmitter inside the central nervous system. And it is what is part of the pleasure response pathway in the brain. There's an increase in the dopamine, and there's an increase of sensation of pleasure as a response to what's going on. Also, serotonin, another neurotransmitter, which is an antidepressant. And so we have the situation where there are patients who have quite significant depression, and they're put on a medication that is a blocker of the process of having the serotonin taken up out of that synapse and put back in the cell, keeping more of the serotonin in the synapse so it has a greater effect on that second nerve in the pathway. And so they are less depressed. That's how the serotonin reuptake inhibitors function. So that's a way of treating depression. And then there's oxytocin. You see, this is a quite complex molecule here. Again, Mr. Evolutionist, how do these complex things come about by random chance events? Well, oxytocin has multiple functions. It is what causes that uterus contract during labor. And if a lady is having very prolonged labor and it's not progressing, the baby's not coming out, then they're given what's called a pitocin drip. It's a form of oxytocin to punt that baby out, to cause those muscles, and the smooth muscle in the uterus to contract and push that baby out. So that's that role. Another role is the secretion of the milk in the breasts. Anti-stress, it actually causes less feeling of less stress. Anti-inflammatory action as well. Inflammation is never a good thing. Also has an antioxidant effect, and that helps deal with many things, including the deposition of cholesterol in the arteries, blocking them. And it also increases relaxation, trust, and overall psychological stability. So it's been dubbed the love hormone. Now, before my wife and I met, I already had season tickets to the Phoenix Symphony Orchestra every year. And then we began to date. I was taking her to the symphony. And see, I had no idea what I was doing her, subjecting her to this love hormone through the classical music. And she married me. Oh, I forgot to mention when I was talking about the increased ability for intellectual function was when I was an undergraduate, every time before I had an exam, I was in my dorm room and I played the second movement of Rachmaninoff's Second Symphony. It's just such a happy, joyful, energetic piece. And I didn't know I was increasing my exam scores by doing that either. So that was very nice. Okay, back to the limbic system, which I mentioned before with that hippocampus. So these are the things that it does. We've talked about memory, we've talked about emotion, motivation makes you more motivated, also deals with the sense of smell, olfaction, processing smells that you're exposed to, and in behavior. So all of these things are dealt with in this limbic system. And so I give my students this acronym here, MMOLBI, to remember all these different things that the limbic system does. After this, there will be a quiz. Can you give this back to me? All right, multidimensional processing. This is another mind-blowing thing here. So the link between structure and information processing is so different to computers. So I showed you the business of the 1010 that computers do. Well, we do multi-dimensional processing instead. So you may remember from high school geometry that a line is one dimension. 2 points determine a line, and that is one dimension. So if you have length and width, that's 2 dimensions, and that gives you the area, in this case of a square or a rectangle. If you have 3 dimensions, that's a cube. So now we have volume, such as how many gallons or liters. 5 dimensions, how do we get to 5? Well, 4, a lot of people say time is the 4th dimension. But what about 5? What about 7? What about 11 dimensions? Our brain processes in as many as 11 dimensions and maybe even more. How in the world does it do it? Okay, there's a great analogy here I'm going to show you. Pay very close attention to the bottom left part of the screen, as different sand castles are going to be built and then dissolved, built and dissolved. So different parts of the brain are being momentarily combined to make these multi-dimensional structures to deal with a certain task and then dissolved. And then the next structure for the next task. So here we go. So this is multi-dimensional processing or representation. Isn't that astounding? This is what you guys are doing right now. All right? Okay. Now, the last mind-blowing thing I'm going to expose you to here is bio-photon. What in the world? Bio-photons. Okay, Most of us are familiar with photons being those little packets of light from the sun. That energy, radiant energy, photons. And so photons from the sun, which are reflected off whatever we're looking at, are what we use to see. And then those photons are processed with the rods and the cones and on through the rest of it back to that visual cortex, and we see what we see. That's not what we're talking about. We're talking about photons that cells in our brain, neurons, produce. So we're producing packets of light inside our head, inside our brain. We don't see them, but under very special circumstances, they were able to discover these. So I'm going to go back and just give you a reminder here of the usual way in which the messages are sent down that axon, that long part of the neuron, that cell that does the work. And so it's that chemical business of ions of sodium and potassium going through special channels, flipping the polarity of the membrane covering that axon, that long part there. And so there you see potassium leaving and sodium entering. So as that happens, the polarity, the electrical direction, positive or negative, flips as this goes along the membrane. So you see here in this first part under the axon that the green part shows that there is the business of depolarization. In other words, what has already been polarized is now reverting back to the resting state. And that middle section is polarization, the flipping of the polarity, positive to negative. And so as it goes along there, you see this change here with depolarization and then repolarization back to the resting state, and then it continues on. So it's a flowing continuous process, as you see there, with those waves. And we'll do that one again here, so that that sequence of depolarization and repolarization occurs in this wave-like function as it goes down. So this is the chemical action with the ions exchanging places through the channels inside and outside of the axon. So that's the usual way in which cells convey that information down the axon. But now I want to show you this business about these photons that are generated not by the sun but by the cells inside. So they made tissue cultures of nerve cells and were able then, under special conditions, to scan and show these photons that were generated by these neurons. This is amazing. But it's not just the brain that does it. Plants do it as well, and even kidneys do it. Whoa. Absolutely amazing. So the question is, why did God create this system? One proposed answer is as a feedback mechanism. See, all these biological processes going in our body have feedback mechanisms, so we know when enough has been done and it's time to stop, so we don't waste resources doing stuff that's not needed. So here you see that forward action potential, referring to that ion chemical means of transporting that signal down the axon towards those synapses to the next nerve. All right? But here we see that inside that blue part, that subsequent cell, you see that little elongated rod with curved ends representing what's called a mitochondrion. And you may know from your biology courses that mitochondria are the little organelles inside cells that use the energy from glucose molecules and convert that energy into a molecule called ATP, adenosine triphosphate, and that molecule is called the coin of the realm, the energy coin of the realm. So the energy that's taken from the breakdown of glucose, sugar, into converting it into ATP, so that energy can be used to drive the other reactions that go on. Zillions of different kinds of other reactions use the ATP, burn it, to get that energy to drive those other reactions. Well, in this particular case, that energy is used then to create these bio-photons, which then go back and give feedback to the first cell that was sending the signal down. So there you see that representation of that wave going from right to left in that pinkish color there, giving the feedback after the initial signal was sent forward chemically. And there is another representation of it showing that bio-photon feedback. Another explanation is that since photons travel much more quickly than molecules, because it's light, traveling at the speed of light, that these distant parts of the brain can act in unison. And that explains the warp speed at which the brain functions, that it functions so much faster than it would otherwise. So here is trying to represent the business of the forward signal using the ions, the depolarization, repolarization, and then the biophoton feedback, so that information can be processed and decide, what are we doing here? Are we doing good, well? Are we doing enough, not so well, too much? But also, there is the business of the biophotons being transmitted not in the cell, but also outside from cell to cell. And that these biophotons are generated at different wavelengths of light. So I think we can understand that blue color is one wavelength of light, red is a different wavelength of light, yellow is a different wavelength of light, orange, the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, these are all different wavelengths of light. And so what's been found here is these biophotons are produced in the ultraviolet, meaning just beyond violet, we can't see, it's a little bit more energetic and faster wavelength. Red, which we couldn't see, and then also infrared, which is just a little bit too slow wavelength that we just pass, just beyond what we can see. And so these three different wavelengths are used to transmit this information back using light to the originating cell. Amazing. Well, how do these photons travel? How are they dealt with? And so here you see the representation of the different colors that are representing the different wavelengths as these biophotons are generated and crossing the synapse there. So one of the things that they're thinking is these biophotons influence the function and the repair of the mitochondria themselves that produce them, so that things can be maintained, that not allow them to fall apart. All right, and as I mentioned, also biophotons traveling from one cell to a different cell, not through the axon, but through the material between cells. Well, inside the axon, it's been determined that these photons travel along the freeways. So you see here microtubules. So our bodies have skeletons made of bone for our muscles and tendons and ligaments and other things to be organized. Inside the cells, we also have skeletons, cytoskeletons, cell skeletons, but those are all made of three different kinds of proteins. One of those kinds are tubulin, alpha and beta tubulin, making up these microtubules. You see the side view and then the end view. It looks like a hollow tube, which it is. Well, those are like freeways inside the cells. And they act as a skeleton for the cell, but these microtubules are also used for transporting things along. And you see kinesin there moving to the right, and you see dynein with an arrow pointing to the left. Those are molecules, very large proteins, that literally are like a part of a body with legs. And they literally burn that ATP and walk along the microtubules You can Google that and see great animations of that happening. And those dyneins and kinesin are carrying sacks. They're like tanker trucks, carrying sacks, vesicles of protein products, of molecules that have been manufactured by the cell to transport them to the appropriate destination with a zip code saying where to go. Well, these microtubules are also used for these photons to move along. And so here you see the kinesin and the dynein with those sacs and the two legs so they can walk along the microtubule. Well, these proteins are made up of amino acids. We use 20 different types of amino acids in our structural proteins. And we have other amino acids that we use in our metabolism that are not part of our structural proteins. And so here are 3 of the amino acids in these proteins, these tubulins that make up the microtubules. And these all have ring structures with double bonds in them. And as I mentioned before, the angles and the corners are carbon atoms. And so these parts that have these double bonds have the ability for the electrons to be able to deal with the photons so that the photons can skip along from amino acid to amino acid at light speed. And so here just again showing you that structure of the microtubule with the side view and the end view, and that these amino acids are some of the amino acids that make up these proteins that make up these tubules. Also, there are these other molecules that have these double bonds and also have the ability with the electrons to use these photons can use to skip along, including these very complex fat molecules here. So I hope you can make out, the light doesn't wash it out too much, that you see all these places where the stone has skipped on the water. Can you make that out? Okay, this is a still shot from a short YouTube video that the world champion stone skipper, one stone, one trip, I can't remember, it was 58 or 85 skips. Whoa. So this is a way to visualize how those photons skip from amino acid to amino acid with those double bonds at light speed, going just like this. It's astounding. Well, these are the things that can happen with these photons. So proliferation is increased. Proliferation means multiplying of the cells. So for example, we have tissues that need to repair. The cells need to multiply, increase their number. Or in growth, so that we can become taller, bigger, larger. Cell migration. We have cells that migrate from one part of the body to a very distant part of the body. Probably the greatest example is on top of our kidney, we have a gland called the adrenal gland, and it makes adrenaline, also known as epinephrine. And this is the hormone that is put out when we have a fright situation, which leads to flight or fight. The instant secretion of the adrenaline or epinephrine, and we're ready to rock and roll instantly. Well, that's because the cells inside the middle part, the medulla of the adrenal gland, migrated from the brain. And it's a continuous nerve all the way down. That nerve grew all the way down there. No synapses until in that gland. So that's how we have that instant reaction. So that's migration. That's one example. We have other examples in our body as well. Growth factors. We need growth factors for tissues to grow. And just one of them, I'll give you an example, is vascular endothelial growth factor. That's a fancy way of saying a hormone that increases blood vessel creation so that there's more blood vessels to serve the tissue. The extracellular matrix. This refers to that combination of fluid and different proteins that are in the space between cells in tissues. So that's needed to be dealt with as well. Inflammation's a bad thing. Well, these photon communications help decrease inflammation. Keep that down. And apoptosis, what in the world is that? That's programmed cell death, purposeful cell death. So if you hold your hand up in front of you, if you would please, during development, it's a paddle. It's a solid paddle. There's no space between the fingers. It's just totally solid. And the programmed cell death is what tells the cells between your toes and your fingers to die so that you end up with individual digits. So that's how that paddle is converted into this. Now, occasionally that doesn't happen properly and someone will have fusion. They'll have something like this. And I'm not going to try and do the Spock-Vulcan thing, but they end up with fusion and these are not separable. So that's what apoptosis does. So this photon communication has a business of decreasing abnormal apoptosis, where it's programmed cell death that you don't want to have happen. All right, so these are the things we've looked at. Perfect optimization, that save wire principle, the tremendous computational power of one human brain greater than the entire internet, phenomenal processing speed, light speed, optimal energy efficiency using only 10 watts just to vegetate and exist. The tremendous capacity for memory, and then the process of how memories are stored, the secretion of the hormones, and we didn't go into all of what they do, that would be a very long time, and the cerebral spinal fluid cushioning and then nurturing the cells it comes in contact with, the location in the limbic system where we play and laugh, the Mozart effect and its effect on intellectual capacity, increasing scores on exams, also more favorable emotional response, calming effect, these types of things. The multidimensional processing, where even it's been shown up to 11 dimensions, where we have these momentary combinations of nerves that are used to deal with the task, and then those combinations are dismantled, and then a new combination for the new task, and on and on and on. And then this bio-photon business, literally light speed operation so that the whole brain can function simultaneously on a particular task. Amazing stuff. So in Romans 12, and do not be conformed to this world, but be transformed by the renewing of your mind. In other words, use that marvelous mind that God gave you, that you may prove what is that good and acceptable and perfect will of God. So evolutionists accuse us creationists of doing bad science and not using our brains. It's actually the other way around. They're the ones dealing with false assumptions and not truly thinking through the consequences of what they're thinking, because everything in evolution is based on assumption and circular reasoning. Assumption and circular reasoning. And they're not really thinking it through, because this is a great time to be a Bible-believing Christian, because we have so much more information and data which shows that we had to have been created by Jesus Christ. There's just no way around it. So people try to deal with that by denying that they were created. You know, there's the verse that refers to, we are fearfully and wonderfully made. And unfortunately, too many people stop right there, because it goes on in the next couple sentences there to talk about how that we, deep down inside, our soul knows that very well. But people do go to great lengths to try to deny that and stifle that knowledge that God put in them. So we're definitely supposed to use our brains. Do not be conformed to evolution, but be transformed by learning how everything in this world was created by Christ. So we have the situation sometimes where, yes, the lights are on, but nobody's home. All right? Exclamation point. All right. So here's a free resource I'd like to make you aware of. On the AZOSA website, Arizona Origin Science Association, azosa.org, we have a series of 18 PowerPoints that go through those 11 chapters, first 11 chapters of Genesis, on a nearly verse-by-verse basis in question and answer format, illustrated by art, various forms of art. And this is understandable even down to the middle, the high school, middle school, junior high, however you call that, grade level. So go to the website, click on resources, and then click on PowerPoint, and then you select your language. It's available in English, Spanish, and Russian. So that's a freebie resource, which is a great way to introduce someone who doesn't know anything about this stuff. AZOSA has also produced 6 DVDs, which we offer back there. The first one is on the Grand Canyon, and it has a great testimony in it about how a particular gentleman, Tom Vale, came to salvation because of the Grand Canyon. Then Dr. Kevin Anderson produced this, we used him to produce this DVD on DNA. And then we had a fellow who was one of these rocket scientist types who could speak in plain English, explaining the relationship of energy and the universe, and how the universe is winding down. That would be the second law of thermodynamics. Then I'm the one who put together this one on what happens at the time a baby is born, the changes, the 5 changes that go on in the circulatory system at the time of birth. What happens, why it happens, what makes it happen, all this kind of stuff. And it has a great story in it as well. Then you all have lots of fireflies around here, yes? Okay, you ought to know how they function, how they make that light, and what they do with that light, how they communicate with that light. So every one of you needs this one on the firefly, all right? And then finally, the last one we just made, also Dr. Anderson, who unfortunately is no longer with us due to COVID, answers the 3 existential questions. Where did I come from? Why am I here? Where am I going? And this is a great one to give to someone who has no clue why they need Jesus Christ in their life. Then one other thing that we have here is a trilogy. The author is a lady who lives in Prescott, Arizona. Excuse me, some time ago, she told me she was writing a book, a biblical historical fiction book, starting with the event of the Tower of Babel, the Judgment at Babel, but dealing with all those first 11 chapters of Genesis using flashbacks, weaving together the biblical, historical people, the patriarchs, and fictional characters, and then factors of everyday life and the overall historical picture. And I thought to myself, how in the world can you do that? Fill up an entire book. Well, she did it. She did a great job. Not only that, she wrote 2 sequels, so there's a trilogy. And I edited all 3 of those books, and I can tell you they are exceedingly well written. You will get science that is woven in, and this is a marvelous way to introduce someone who likes to read but is not a scientist and doesn't have a special interest in creation. They'll get that message and the message of salvation in these books. They are fantastic. So that's the end of the Brain Talk.